So in this video, I wanted to finish up with some issues affecting solubility. All right. So factors affecting solubility. All right. So what are some things about solutions that might affect whether, first of all, whether or not something will dissolve, and second of all, how much of something might dissolve. All right. The first is going to be what I call the polar or ionic nature of the solute and solvent. All right. And this topic is what a lot of people refer to as this concept of like dissolves like. All right. So if you want to make a prediction about whether or not a particular type of solute will dissolve in a particular type of solvent, chemists often use this term like dissolves like, which means that things tend to like to be dissolved in things that are similar to them, that are chemically similar. All right. And so let's start off with a couple of basic observations. All right. And these are some materials that you should be somewhat familiar with. All right. Even though I call this one chemical right here hexane. All right. Just remember, it's very similar to gasoline. All right. Hexane is a molecule that's got 6 carbons in it. All right. Gasoline it's actually a mixture of molecules, but most gasoline molecules would be about 8 carbons long. So if we extended this chain of 6 carbons by 2 more carbons, making it a chain of 8, that would be very similar to what gasoline is. All right. So we're going to compare that to water. All right. So we're going to take 3 things that are representative of different types of materials. All right. So we're going to use an ionic compound, and most common one of those is table salt. We're going to have a polar covalent compound. Sugar would be a good example of that. And then we're going to have a non-polar solute, all right, which is wax. All right, so if you just took candle wax and just scraped off a little bit of it, that's called paraffin wax, and that would be a very good example of a non-polar material. So, first of all, we know that salt will dissolve in water, but if you took a little bit of salt, and not that you've ever done this, but if you were to drop that into a little bit of gasoline, all right, it would not dissolve. The salt would just sink straight to the bottom of the cup of gasoline, all right? Sugar is going to behave the same way. We know that sugar dissolves in water, but if you put some sugar into gasoline, it's going to sink straight to the bottom. It does not dissolve, all right? The thing is, candle wax is going to behave in the exact opposite way, all right? If you took a little candle wax and dropped it into gasoline, you're going to see that it dissolves almost immediately, all right? So it would look clear, all right? But if you take candle wax and you put it into water, it just floats there, all right? So the thing is, we see the opposite trend for wax as compared to these other materials, all right? So the explanation for this lies in whether or not a compound is either polar, non-polar, or ionic, all right? And so the concept is that things tend to dissolve in things that are somewhat like themselves, all right? So to share this, I'm going to break this down into a couple of different, so on top here, I've got the 3 possible solute categories. We've got a non-polar solute, all right, examples would be wax or oil. We've got polar solute, examples would be things like sugar or alcohol. And then we've got an ionic solute. So an example would be sodium chloride, all right, just salt, all right. And on the bottom, we've got 2 different types of solvents. We've got a non-polar solvent. We're just going to say gasoline as an example. And then a polar solvent, all right, and water is going to be the classic example of that, all right. So notice that whenever the material is the same, polar solute, non-polar solute, non-polar solvent, that's going to be something that dissolves, all right? So the green arrow would mean that dissolves, all right? Also over here, polar solvent, polar solute, that dissolves, all right? The thing is that ionic solutes will also generally dissolve in a polar solvent because both of these, both the polar and the ionic compounds are things that have charges on them. So even though the word ionic is not the same as the word polar, remember that an ionic compound like sodium fluoride, it's comprised of things that have charges, all right? The ions, the sodium ion has got a +1 charge, the chloride ion has got a -1 charge, all right? But for a polar solvent like water, all right, remember this bond here is polar, and that means that the oxygen has got a delta negative on it and the hydrogen's got a delta positive on it. So even though it's not a full -1 charge and a full +1 charge, there still are some slight charges on this molecule. All right, and so an ionic something would have something in common, something that's alike a polar molecule. All right, and so that's why it tends to dissolve. All right, so the opposite of some of these things are also true. So a polar solute is not like a nonpolar solvent. All right, so that tends not to dissolve. That's why I'm using a red arrow for that. All right, and also an ionic solute is not like a nonpolar solvent. Those tend not to dissolve either. All right, but then we have a nonpolar solute over here and a polar solvent. This tends not to dissolve. All right, so you get green arrows between solute solvent combinations where they're both similar to each other, but you get a situation where things don't dissolve whenever their properties are different from each other. All right, so this little concept is summed up in the phrase "like dissolves like," which means that things tend to dissolve in things that are similar to them. All right, and what this means that compounds with charge character, which would include both ionic compounds like this, and I should say here, so ionic and polar covalent compounds, those would tend to dissolve in each other. All right, but these types of compounds would tend not to dissolve in compounds that don't have any of that charge character. And when I say things that don't have charge character, I'm talking about nonpolar covalent compounds. All right, so for example, if you look at hexane right here, this is not a polar compound. There are not any polar bonds in this whole molecule. All right, so I can't draw any delta plus delta negatives on any of these molecules right here in the same way that I can do for water. All right, so that's why it's characterized as being nonpolar. And so the opposite of this is also true, that compounds that lack this charge character, nonpolar compounds, tend to dissolve in each other. That's why wax would dissolve in gasoline. Another example would be if you took a little vegetable oil and put it in gasoline. You would expect that would mix as well, all right? But if you put either gasoline or vegetable oil and you mix them with water, they're not going to dissolve because that's mixing a polar something with a nonpolar something, and those just aren't going to make solutions. So another factor that affects solubility is temperature, all right? And there's two trends that are commonly talked about, all right? And one has to do with the solubility, the general solubility of a solid solute in a liquid solvent, all right? Something like salt water or sugar water, all right? And what happens there is we generally find a trend of upward solubility, all right? What this means, so remember, solubility is the amount of the solute that would dissolve. So it's going to be the maximum amount of the solute that you could dissolve at a particular temperature. So what this means is that you can dissolve much more of a solid in a liquid if you get that liquid hot, all right? So the thing is, this is going to be opposite of the trend that you tend to have when you have gases in liquids, all right? Whenever you try to dissolve a gas in a liquid, you actually find that you can dissolve much more of the gas at a colder temperature. All right, so the trend tends to be a little bit more downward like this. All right, and what's one common example that we would have of this is what happens when you leave a carbonated beverage out and let it warm up to room temperature. All right, so if you had some Coke and you just left and it's cold and you keep it cold, let's say you put it back in the fridge, all right, and you compare that to an identical glass of Coke where you leave it out on the counter, all right, which is going to hold on to its carbonation longer, all right, the cold stuff, all right, the cold stuff is going to keep that fizz for longer. The warm Coke is going to go flat pretty quickly, all right. Another example of this is what happens when you have a pond, all right. We know that fish depend on being able to breathe the oxygen that's in the water, all right, and you can actually dissolve a lot more oxygen in cold water than you can hot water, all right. So fish, as far as the fish is concerned, a lot of fish prefer that colder water because there's a lot of oxygen generally dissolved in that water. In the hottest part of the summer, the pond water warms up. It can't dissolve nearly as much water, and sometimes this can cause some issues for fish. Moving on. So the next factor is something that only is going to apply to gases dissolved in liquids, and that's pressure, all right? So in general, you can dissolve more gas into a liquid at a higher pressure than at a lower pressure, all right? And the classic example of this is going to be what happens when you open up a bottle of Coke, all right? So let's say that you've got some capped carbonated drink, all right? Before you open up that vessel, all right, if you just look at the liquid inside, you'll see it's clear. You couldn't tell that it's carbonated, all right? And that's because when you do this, it's under a high amount of pressure. So in that space below the cap and the liquid, that is high pressure carbon dioxide, all right? And if you feel the bottle, if you squeeze it, you can feel that it's under a lot of pressure, all right? And what that means is that this liquid below there, so that's going to be at a higher pressure, so there's going to be a higher solubility of carbon dioxide. So this is dissolving a lot of carbon dioxide. So what happens when you open it? All right, you release that pressure. All right, so this is now low pressure, and we're at what I should say atmospheric pressure. And at that pressure, the liquid can't dissolve as much of the carbon dioxide, and so you immediately see the formation of some bubbles. All right, and these bubbles are forming because that is the dissolved carbon dioxide, which is in the liquid, becoming undissolved, and that's when it makes those bubbles. All right, remember, the bubbles that you see in carbonated water are not dissolved in it. All right, so each of those bubbles, would contain literally millions of carbon dioxide molecules, and that happens because of this relationship between pressure and solubility.